Hi everyone, welcome back. Today we're going to be talking about convolutions. Before we get started, some announcements. Homework 1 is due next Wednesday, and then quiz 2 is due on Monday, so be sure to do those. And the agenda for the day, we'll be talking about computer vision in general. In the beginning, we'll talk about how we represent images and why multilayer perceptrons don't work well on them, and then we'll dive into convolution mechanics. So yeah, first of all, what is computer vision? And the way I define it is computer vision is a field of computer science focused on processing, analyzing, and understanding visual data. And visual data is kind of a broad term. It can include images, but also video, maybe 3D scans, and so on. Some examples of tasks that we'll be covering in the next couple lectures include classification, where we just predict a class for a given image, what object is displayed in that image. We might add localization to it, so what object is portrayed in the image and where is it. And then as we move into multiple objects, we go into object detection, where we just predict bounding boxes around objects, and instance segmentation, where we might do a dense segmentation of where each object is and so on. And then going into the history of computer vision, it kind of starts off very interestingly. In 1959, Huber and Wiesel were experimenting with the visual cortexes of cats. And so what they did is they plugged in electrodes to read brain signals from cats, and they were showing it different images, and they were showing it different things, and then they weren't actually getting anything. And then one of their plates that they were showing slipped out of the projector, and it showed a slanted line on the projector screen, and they were getting a lot of readings from the electrodes. And so what they found is that the early stages of visual cortexes process very simple structures such as edges or lines first, and then kind of hierarchically going into kind of more complex structures, detecting kind of shapes and objects and so on. And this work eventually earned them a Nobel Prize. This also motivated the way we did object classification and object detection, just computer vision in general. In the past, prior to 2012, we would design hand-engineered features such as Sift, Hawk, Daisy, etc., to detect edges and kind of other features in images. And then we would use support vector machines to classify kind of what object and image would belong to. But after 2012, with the explosion of deep learning, we were able to replace all of these hand-engineered features and these complicated pipelines with deep neural networks that learned important features better and had a lot more flexibility and just caused a massive acceleration in the progress of computer vision. And the way it started is in the 1990s, when Jan LeCun proposed one of the first versions of convolutional neural networks to detect, not to detect, but to classify digits and to read postal addresses. However, it was very shallow, very small, and very slow because compute was not kind of easily available at that time, and we didn't know how to utilize it properly. And the real explosion happened in 2012 with Alex Krzyzewski and with AlexNet, which achieved a 16.4% error rate on ImageNet, which was ridiculously good at that time. And they did it through being able to write really efficient GPU kernels and being able to utilize GPUs for training neural networks. And that allowed them to use kind of a lot more compute and a lot more data to train neural networks. And since then, we kind of just took it to further and further levels and developed better models. Over the years, if you look at kind of the history of ImageNet, we see in 2011 with the state results at that point, we were getting 26% error. But then in 2012, we achieved 16.4% with AlexNet, and since then we were just developing better and better deep neural networks, and nowadays we get a sub 1% top 5 classification error in ImageNet. And yeah, we'll probably just keep improving. So how do we represent images as data? If you know how an image is represented, it's nothing more than just a 2D array of pixels, and each pixel is kind of a feature. So for grayscale images, these features are going to be 8 bits, and they're going to be kind of from 0 to 255, kind of just the number that represents how bright a pixel is. So it's just going to be a 2D matrix that we represent in data. For colored images, we it's basically the same thing, but now we have three channels for red, green, and blue, and each channel is represented by a 2D array of like pixels, right? So each pixel is going to have three features now. And so for colored images, we have 3 times as much data, and the shape is also going to be three-dimensional. So we're going to have height, width, and then the depth or the number of channels as well. And so why do multi-layer perceptrons, kind of as we learned, like densely connected neural networks, not work well? So first off, let's think about this. Let's say we have a 200 by 200 by 3 image, so it's a 200 by 200 RGB image. And so in total, it has 120,000 features because you can manipulate each color of each pixel to generate a slightly different image. And if you want just a very shallow, very simple neural network with only 10 hidden layers, we realize that we need over 1 million weights to train this. And with 10 hidden units, it's not going to actually learn very much. So first of all, densely connected neural networks are very inefficient for image data. We just need way too many weights, and it will be way too difficult to train anything that's actually going to learn something useful. Another reason is let's think about it a little bit intuitively. So how do we convince ourselves that an image contains an object X? So let's say we look at this image, or these two images. We look at kind of like what features at a high level like does this image have? So we see like, oh, this object has like an oval-shaped body, and then it has like a long white neck, and then it has like a long beak and like a head like that. Or maybe in the other image we see like, oh, this object has kind of like spread out wings, and it's like over water, and it has this kind of like elongated beak, and so on. And so the takeaway from this is we look at local regions of an image. And so the basic idea is if we design neural networks that can operate on local regions of an image rather than individual pixels or like on faraway pixels or just the entire image at once, we can design a much more efficient and a much more intuitive architecture. The densely connected neural network doesn't work well because for each hidden layer, we consider all of the pixels in an image. And so that's very inefficient. And it's very much not kind of how we as people interpret images and how kind of visual and Huber and Wiesel developed an intuition of like the visual cortex. And so the second reason is we need to have some concept of locality in our hidden features in a neural network for computer vision. The same ideas have been applied in classic computer vision as well. The Kenny edge detector, for example, works by detecting gradients in kind of in locality on like nearby pixels in an image, and using that you're able to detect gradients, kind of like detect where the edges are. It does not look at all of the pixels in the image at once. We have like a small filter that slides over an image and detects gradients that way. And so the other thing is that deep learning is a process of extracting hierarchical representations from an input. And for an image, that means first detecting edges, textures, and colors from bare pixels, and then using those to detect slightly like more complicated shapes and patterns in intermediate layers. And then lastly, maybe combining those shapes, patterns to detect abstract high-level features such as like facial shapes and high layers, or maybe like objects or something else. And lastly, some other desirables that we want is, first of all, equivariance to translation. What this means is that for the same set of pixels, when translated, we should have the representations translated as well. And so you can see it in the diagram on the right. If we move the cat, that means that our features in an image should also be moved in the same way. So that's translational equivariance. And lastly, and second, we also want translational invariance. And so that means if we move the pixels in an image, the output or the semantic meaning should not change. And so on the left image, you see that as we move the cat, it's still a cat. So that's nothing changes in the label in that sense. So that's called translational invariance. The multi-layer perceptrons or densely connected neural networks do not follow this assumption because each pixel is going to be densely connected to some neurons, and if we move an image very slightly, all the pixels, all the features are going to get just completely shuffled, and our intermediate representations are going to be completely different. And so the solution we come up with is convolutional neural networks. So convolutional neural networks typically have two main parts of a model. So first of all, we have the backbone, which learns kind of features through a bunch of convolutional layers, pooling layers and activations. And then we flatten it and we feed it into some head. And so the head is, in this case, going to be like a classification head. And that's taking that kind of intermediate feature, latent, as we call it, and actually kind of classifying that and getting it into an output that we want. Often we can reuse the backbone because that learns kind of fairly general features, and we can just swap out the head to perform some other task or some other sort of classification. So convolutions, diving into kind of how they work. At a high level, instead of processing the entire image at once, we want to process patches of it instead. And so that's going to allow a network to pay attention to local regions of an image instead of looking at faraway pixels. And second, we want to process each patch with a layer parameterized by the same weights and bags. So this is called weight sharing. And so this will ensure that every single patch that we process is going to output the same representations if the patch is the same. And second, it's going to preserve translational invariance and equivariance. So the way this looks like is we have a weight filter, which we also call a kernel, that slides over an image and it generates our convolved feature. The actual step of how to perform a convolution is, first of all, take the kernel, slide it along the width and height of by a certain amount, which we call the stride, and then we compute dot products between the entries of a filter and the input at any position. So let's look at an example. When we take this kernel and we put it over the red region in the image, we see on the left side it's going to produce 10, 10, 10, which is going to sum to 30. And on the right side is going to produce negative 10, negative 10, negative 10, which is going to sum to negative 30. When we put everything together, we see that at this location, it should produce an activation value of 0. As we slide over, we see that on the right side, everything is going to sum to 0 now. So it's going to become 30. As we keep going, we see that this convolution produces this kind of activation. And so what this filter does is it detects vertical edges. The reason intuitively kind of the way to look at it is if you look at the values in the filter, we see that it looks for kind of differences in the patch between the left side and the right side. And so when it goes over a flat kind of segment in an image or kind of a smooth region in an image, the left side and the right side of the patch are going to have very similar values and they're going to cancel each other out. When there is a gradient in the patch, the difference is going to get magnified and going to get, and there is going to be kind of an activation at that region, so we're going to detect vertical edges. So taking